Swayam Prabha. Digital India. Educated India.
Thermodynamics, being presented by Tagore International School and Scottish High School. We will start with Team A of Tagore International School, comprising of Tanisha Singh of grade 12 and Atharv Gaur of grade 12. Let's welcome them on stage.
Namaskar, Abhinandan, Adab.
I am Tanisha,
And I am Atharv.
and you must imagine yourself in this.
Tum kya mile? Tum kya mile?
In the valleys of J&K. And unlike Miss Bhatt, you can actually feel the cold and see your life flashing by the second. Now you see two benches, one metal and one wooden. Which one would you never sit on even if Karan Johar gave you his entire will? Obviously, the metal one.
We need a volunteer.
Anyone? Come on.
Would you be kind enough to please feel these materials for us? Which one do you feel is cooler?
Yeah, as in which one? Temperature-wise. That one. The metal?
Metal one? Why is it so? Is there a temperature difference in this room? No? This is because this metal ruler is a conductor. When you touch this material, heat flows from your body into this material, and hence you feel it is a little bit cooler. Whereas this coaster is an insulator. When you touch this material, there is no heat flowing from you into this material. Hence you feel it is relatively warmer. Thank you. That is thermodynamics to you. Thermo means heat. Dynamics is the study of motion. So thermodynamics in one basic question is, how does heat travel from one place to another?
Now, two keywords to be remembered at all costs. So let's say we are talking about you right there. So you become the system and everything apart from you becomes your surroundings. A thermodynamic system is a very large collection of particles having a certain temperature, pressure and volume. In short, Raj is the system and Ja Simran Ja having an effect on him becomes the surroundings.
Open, closed, and isolated. These are the three types of systems.
Wait, did you just say systems?
No.
It's time for मेरी गली में गली 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 में हम मेरी गली में गली 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 में तेरे सिस्टमों का रास मेरी गली में मैटर एनर्जी का स्वैप ओपन सिस्टम में हम मेरी गली में गली 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 में हम मेरी गली में गली 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 में बंद सिस्टम की है बात मेरे गली में एनर्जी होती अंदर बाहर मेरी गली में मेरी गली में
So basically what this girly girl is trying to say is, if you have a hot cup of coffee and you keep it outside, you can see vapors coming out of it and it will get cooler. So there's exchange of heat and energy. This is an open system. Now let's cover this with the coaster. There are no vapors coming out of it, but it will still get cooler. So there's no exchange of matter, but there is exchange of energy. This is a closed system.
Well, first, gully girl idea was much better than that. And second, this must give you a very vague idea about what an isolated system is, right? To help you understand better, we've got some desserts for you. But first, volunteers again. Come on. Hello. Okay, we want you to fill this container for us.
All right.
Okay. Is it warm?
Yes.
You too. Fill this container for us. Is it warm? Yes. So if this is warm, the box also inside this container would also be warm.
Must be.
Right? Okay, then we've got some hot desserts for you, both of you.
Is this for us?
Yeah. Go ahead. Don't be shy. Have it.
Seriously?
Yeah.
Wow. What is to open?
Go ahead.
If you want to eat, you need to open it.
Very nice.
It's cold, right?
Yes.
First of all, hot ice cream should not exist in your dictionary.
That's a cool line.
Second of all, ever wondered how grocery apps are able to do just that without getting 1-star reviews of ordering ice creams and getting milkshakes?
Okay, got it. Yeah, continue.
No idea?
No idea.
Okay, well, thank you. You take ice cream. Yeah, okay. That's because these grocery apps use insulated ice cream pouches based on this exact concept of thermocol box. So, in this insulated ice cream pouch, there are 2 plastic layers, and between those 2 layers, there's a cotton-based panel, insulating panel, just like this thermocol. It has small air pockets in them that does not allow the heat to travel across the pouch. So the ice cream remains cold and does not lose energy. And of course, it's not losing any matter, right? That's why in isolated system, nothing gets exchanged, neither matter nor energy.
Complete isolation is a
A
no,
no, not
possible.
possible.
Now, let's say in the morning when we first placed the ice cream in this box, it could be around minus 12 degrees Celsius. And now it has increased to minus 10 degrees Celsius. Even if we can retain 80 to 90% of energy, we would still call it an isolated system. But again, complete isolation is a no, not possible.
This brings us to the mastermind, the Thakur, the Vijay Salgaonkar of this movie, an adiabatic process. Now, in an adiabatic process, let's say we burst this balloon. This is an example of just that. How so? Tell me, do you feel any temperature difference in this room because of the burst?
I don't think so.
Okay, and well, there is no exchange of matter. Therefore, in an adiabatic process, nothing is exchanged, neither matter nor energy between the system and the surroundings.
Since complete isolation is a no, not possible, hence no process is a 100% adiabatic process.
Yet, it can occur in isolated systems like ice cream pouches. All these ice cream pouches or even thermos flasks where adiabatic processes can occur are called insulated containers. Many examples like the ice cream pouch we told you about,
Thermos flask, ice and ice box.
or even bursting of a tire, because the process is so quick, the heat cannot get transferred and there goes a pop. That is the adiabatic process to you, where nothing gets exchanged, neither matter nor energy.
Just like us and the knowledge around us. No.
Yes. मेरी गली में गली 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 में, हमेरी गली में गली 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 में, चलते बोल के अदाब मेरी गली में, हाँ चलते बोल के अदाब मेरी गली में.
We thank you for being such a wonderful audience. Thank you, everyone.
Why so mean?
Let's now welcome Team B, comprising of Shri Krithi of grade 12 and Priyanka of grade 12 as well.
Namaskar, Adab, and a lovely morning. We welcome you to our daily science shenanigans, another day of the program known as Life. Today, we're going to cover the topic
Thermodynamics.
exactly. So keep your ears open and we hope you listen carefully.
To get started, we have a rap prepared for you in this topic and we're gonna freestyle it, baby. Let's go. Yo, it's entropy, shady, dropping science like it's hot. Laws of thermodynamics, ain't no time to talk. First law, energy's a sneaky snake. Caught, transform, change form, but the total never caught. Second law, entropy is queen, the chaos commander. Order to disorder, ain't no time to meander. Ice melts in your drinks, castles crumble to dust. Entropy is marching on, ain't no room for trust. Zeroth law, the chill, master temperature's the key. Two system touching up, balance in decree. Same feels no flow, ice like ice cubes in your tea. Entropy sleeps tight, ain't no need to decree. Third law, information's the code, the hidden thread. Entropy's whisper in patterns, it's red. Closed system, isolated secrets they keep. Entropy's knowledge locked in sleep.
That certainly was great. Thanks, Phoebe. Moving on to the first lesson of the day, the first law of thermodynamics, also known as the law of conservation. It basically states that energy is neither created nor destroyed in an isolated state. It can only change its forms. Let's imagine a magical energy ball, which you can just pass amongst your friends. You can catch it, throw it, or even transform its shapes in different shapes. But you can't just vanish it or like make it disappear or create it out of thin air, right? Imagine it as a game of hot pocket. wherein the energy is always constantly changing, but it never really disappears, does it? Let's take an example.
A bicycle ride.
Genius. When you pedal a bicycle, your body converts the food that you ate from chemical energy into kinetic energy, which propels the bike forward. Hence, the energy is never really lost. It just changes from one form to another. Speaking of food, by the way, another example is baking cookies. When you bake cookies, the energy from the ingredients that you use, like sugar and flour, are converted into heat energy, wherein the cookies are baking in the oven. So no energy is lost. The total energy really remains the same. It just converts into heat.
Wow, I never thought there could be science behind something so tasty.
Exactly.
Why do you ruin cookies for me?
Okay, I'm sorry. Let's move to the second lesson. Second law of thermodynamics. It states that energy, whenever there's any transfer of energy or transformation, whenever there's a transfer of energy or transformation, the entropy, there's always an increase in it of the total system and the surroundings.
Wait. Entropy, system, surrounding? Explain.
Okay, I'll explain. See, a system is any individual object, anything basically. You can be a system, I can be a system, the audience can be a system. And the surroundings are what comprises, what surrounds the things. The system, you're a system, and the surroundings, they're the surroundings. Got it? Now moving on to entropy. Entropy is a way of measuring randomness or disorders that take place in a system and surroundings. In simple terms, basically, you know how as time increases, the things, they tend to disorder or disintegrate, gets less structured. That's what it means. Like, an example could be tidying a room. Without cleaning it regularly, your room will, of course, get tidy, messier, day by day. This law is basically the universal law of keeping your room tidy. That's a law. One example could be...
Oh, I'm tired of thinking of examples. Makes me want to eat ice cream for some reason.
Genius. Ice cream could be an example. When you hold a ice cream cone on a hot sunny day, the ice cream drops down your hand, separates, gets less structured, and then the melting process basically increases the energy and the entropy of the ice cream as it transitions from solid state to a liquid state.
Our last lesson is the third law. It states that as the temperature of a system increases or reaches to an absolute zero at 0 degrees Kelvin or minus 213.15 degrees Celsius to be precise, the entropy of the system reaches a minimum value. It means that as she explained the second law, converse to that, as things get colder and colder, they become more ordered and organized, maybe even reaching a state of perfect order at absolute zero. It's like trying to clean an untidy room so spick and span that there is no dust particles anywhere. Everything is arranged and at its place. But unfortunately, unlike our dreams, even that perfection is not achievable due to human errors, natural errors, or other causes. Let's try to think of another example.
Forget examples, I really want to solve a puzzle.
Oh, great, a puzzle. Imagine trying to solve a jigsaw puzzle on a super cold day. As the temperature decreases, the loose pieces get fit more neatly, and you have eventually a puzzle with no loose pieces or misfits.
I really didn't think my guess would be correct. See, I told you I'm a genius.
Consider yourself lucky.
Thank you.
Thank you so much.
Presenting on the topic thermodynamics, we call upon Team A, comprising of Sanvi Kumar Verma from grade 11 and Ojas Jain from grade 11 as well. Let's welcome them.
Good afternoon, one and all present here. To the respected teachers, the esteemed jury, and all my fellow presenters. My name is Sanvi Kumar Verma, and today I, along with
Ojas Jain,
would like to present to you the basics of thermodynamics and how they function in our day-to-day lives. Whether it's rubbing our hands together to keep us warm in the winter, or even traveling by car from one place to another, or so much so traveling from a train from one place to another. What is the law of physics? What is the branch of physics that dictates all of this? Today, we would like to present to you this. Now, I would like to hand this over to Ojas Jain to explain what is thermodynamics.
Thermodynamics is the branch of physics that relates many physical quantities, including work, power, and energy. We will explain thermodynamics using car engines. Sun will explain how a car engine works, and then we will show some experiments.
Right. So we've all sat in a car before, and while we've all thought about how the car moves, we've never really thought about how the engine functions. Now, there are two types of engines that are prevalent, a 4-stroke engine and a 2-stroke engine. The one that we want to present to you today is a 2-stroke engine for the sake of simplicity. Now, this is an engine right here. The one that you can see right here is called a carburetor. This is called a throttle valve, and that is the piston right here. This is the arrow, and this is what governs the engine. Now, in this cylindrical vessel, there are two tubes. One is an inlet outlet, and one is an external outlet. Now, when a fuel is attached, fuel enters from here and air enters from here. The air and fuel then combine together in the carbonator, get compressed, and then work their way through the throttle valve. Once, assuming my hand is the fuel itself, they enter here, travel here, get pushed by the piston, and then travel upwards through this transfer tube. This transfer tube helps the valve, the fuel, come right here, enter into this tiny notch, and then get upwards compressed. Once the gas is compressed, there's a spark plug that is here, and that explodes or combusts the gas itself. Once that is done, knowing basic physics and chemistry, once the gas is compressed and combusted, smoke is created, which then travels downwards through the outlet tube. This process continues on and on. But then the question arises, will there always be a sun turning the wheel around and around? Not really. There's a process of momentum that takes place. Once it takes place over and over again, momentum builds up and it keeps moving on. Since we couldn't bring a real car engine here, this is a demonstration demo.
The car engine follows the basic laws of thermodynamics. The first law states conservation of energy. Conservation of energy is basically, which we've all studied, it states that energy is never created nor destroyed. It can only be transformed from one form to another. In a car engine, energy converts from chemical energy of the fuel to heat energy of when the explosion occurs, and mechanical energy which moves the piston down and finally rotates the crankshaft. The second law governs entropy. It states that entropy in an isolated system always increases or remains constant. In a car engine, it determines the efficiency of the engine. Energy is lost in the form of heat to the surrounding car parts and thus lowers the efficiency. Now we will show an experiment
But before that, what is the difference between entropy and thermodynamics and mechanics? If both of them deal with motion, then what is the difference? The basic difference arises that mechanics deals with the motion of a body as a whole, whereas thermodynamics deals with the internal movement of the particles. Now, taking an example, let's, assuming this is a gun, shoot. The bullet that moves out travels and moves across a given space and across time. However, it is not really affecting the temperature around it. But let's say this is a wooden panel and it hits the wooden panel, then it absorbs and reflects out temperature, thus changing a level of temperature around it and that of the wooden panel. And that is the basic difference between thermodynamics and mechanics. Now we would like to present to you a small demonstration using a chemical experiment wherein we take NaOH pellets, that is sodium hydroxide, and then we mix it with water in order to create aqueous NaOH. Now, the reaction that is taking place right here, right now, or what we are about to explain to you, is when we mix NaOH with an amphoteric metal such as aluminium, there is the creation of NaAlO2 and H2. H2 is a gas that will serve us to understand the first law of thermodynamics, that is the conservation of energy. Now, this gas later will be tested using a pop test. Now, please have a look. This is a redox reaction. That means there is reduction and oxidation going on simultaneously.
Yeah, add the aluminum.
adding tiny little balls of aluminium into the aqueous NaOH.
It will take some time to react as this is a slow reaction, but once it starts, it's exothermic and it is very fast. Just wait. Just hold the top. Cover the top so that the hydrogen doesn't escape. We can already see
slight bubbling happening, which is a proof that there is hydrogen bubbling or some gas, which we will prove right now.
Yeah.
And that's a pop test. You can still see how fast the reaction occurs, and this is called a redox reaction and an exothermic reaction.
Just leave it.
Okay. And that is the basics of thermodynamics.
Thank you so much.
Thank you so much.
Okay, finally stop.
Yeah.
We now welcome Team B, represented by Gangesh Agarwal of grade 12 and Prakhyat Sinha of grade 12. Let's welcome them.
Good afternoon, ladies and gentlemen. We are students of Scottish High International School, and today we will be demonstrating a presentation on thermodynamics.
So before we start, we need to get an understanding of what is thermodynamics. Thermodynamics is the branch of physics that deals with everything related to thermal energy. That would be the system's internal energy. That could be how two different objects with a difference in thermal energy interact with each other. And we're going to explain one of the 4 laws of thermodynamics using this model right here.
So this is a model which which demonstrates the mechanism of how a vehicle brakes. So over here, the first law will be used, as he stated, that energy cannot be created nor can it be destroyed. So over here, as you can see, that the disc over here represents the brake disc. We have a lever system over here to demonstrate how the brake calipers work. So brake calipers are the bright orange parts that you sometimes see on the tires of sports cars or motorsport vehicles. So what happens is that whenever we apply brake pressure, those calipers start to interact with the brake disc, which causes friction and allows for the motor to slow down. So first we will give the demonstration and then we will explain it further.
Right. So as he explained, the disc will be our brake disc and this lever here would be our brake caliper. Right. So we're going to assume that there's a car that is traveling at really high speed. The brake disc will be spinning at approximately the same speed as the tires of the vehicle, and I'll be releasing the lever so that the brakes are applied on the car in 3, 2, 1. So as you can see, the brake caliper has helped the car to come to a stop and rest.
So now you must be wondering, where is the first law of thermodynamics being used? So if we, because this is just the mechanism, so we want you to imagine a whole tire that is right now around this brake disc and brake caliper system. And now what happens is that the kinetic energy that was generated due to the spinning of the motor, the spinning of the disc, that is now being transformed into different forms. So one of the major forms that it's being transformed into is heat, thermal energy. And now what happens is that thermal energy is absorbed by the immediate surroundings of this brake disc, which in our case would be the tires. Now what happens is, we all know, as thermal energy is increased in a system, the temperature rises. So obviously the tire temperature rises due to this whole process. Now that heating of tires is a concept that is widely used in motorsports. What happens is that due to the increased tire temperature, the grip levels of the tires increase as well, which provide better speed and better control of the vehicle.
Another popular application of this is ABS. This is anti-lock brake system. Basically what happens is, whenever we have a spinning disc, I can obviously hold on to the disc and let it stop completely. But that wouldn't stop the car, that would just stop one of the tires. The rest 3 tires and the car itself will keep moving forward until it comes to a stop. That is what we call as a lockup. Each tire can lock up individually. That happens when the brake has applied too much pressure, too much friction, as if that particular brake disc has stopped, but the whole vehicle hasn't come to a stop. This is a very prominent problem in motorsports, such as Formula 1. To combat this, we have anti-lock brake system that in real life cars, these effectively apply brake pressure so that the maximum braking can be achieved without locking up any of the tires. However, in motorsports, since this isn't there, what drivers like Max Verstappen do is they use trail braking. All they do is they go to 100% brake application initially, but then bleed off the brake pedal as they start to enter the turn-in phase. So we can explain this using the grip limit of the tire. Since the tire has a particular grip limit, you cannot exceed that. If you do, you will lock up or you will oversteer. So to be within that limit, you can either use 100% of the brakes or you can steer 100%. So if we use a combination, for example, 70% braking on 30% steering, you can slow down the car while moving in a circular path. This is what is utilized by Formula 1 drivers to go quick around the lap. And this is how ABS is artificially used by Formula 1 drivers, while in real life cars, we'd rather use the electronic system that we have in place. Taking this further, in case that the driver misjudges the braking point, if he goes a bit too quick into a corner, he will lock up the tires. This was evident in Azerbaijan 2021, when Lewis Hamilton, who was priced to win this Grand Prix, locked up the tires and went straight on in turn 1, while the turn went left. That ended his race and he finished last in that race. Similarly, Charles Leclerc, he encountered a different problem. This is similar to what we call as locking up. His two tires, one had a brake temperature of 100 degrees higher than the other one. This difference in thermal energy caused the brakes to not be effective. And if this was the case in real life, our ABS would take over in the ECU. But since this is Formula 1, Charles Leclerc couldn't cope up, because either he could take care of all the 3 tires, or he would have to slow down just to take care of that single tire locking up continuously throughout the corners. So that is why he couldn't win that race and he finished P4.
I think there was one last example that we were talking about. The recent Australian Grand Prix in 2024, where the current world champion Max Verstappen also had to DNF, did not finish the race. And I think that happened because of his brake discs were heating a lot. And what happened was, because the friction was being generated a lot, considering beyond the calculations that were expected, the friction generated was a lot due to the high track temperature and the high internal energy that was being generated. That's why the tire around the brake disc started to melt as well. The rubber was melting, which caused his car to seize up at different turns, which we explained as before was locking up.
So linking all of this back to the first law of thermodynamics, we can see that if you have excess thermal energy within your brake disc and then you apply the brakes, it is highly possible that you would either slow down really slowly or you would lock up the tires, which would lead to more excessive corrosion of your rubber in the tires. And this is not what we desire, and henceforth ABS plays a crucial role in our daily life and helps us for safety. Thank you.
With this, we complete the presentations on thermodynamics.
And now it's time for the judge's opinion.
The runner-up is Tagore International School, Delhi. The participants are Delisha Singh and Atharv Gaul.
And the winner is Scottish High International School. And the participants are Sanvi Kumar Verma and Ojas Jain.